Welcome back to another episode of Introductory Organic Chemistry. Except from now on, we're not going to go with introductory anymore, as the topics that we're starting to discuss are becoming quite advanced. Today we're going to talk about hydroboration and 1,2-boron metallate rearrangements. But before we get into that, let's go through the practice problems that I assigned last lecture. So in this first problem, we have a multi-step synthesis where we have to fill in the blank. So initially, we have this TMS enol ether, which reacts with methyl lithium to generate a lithium enolate. This lithium enolate is then able to do an aldol addition on this aldehyde, giving us this beta-hydroxy ketone product. This is then able to be protected using TBS chloride and imidazole to afford the TBS-protected carboxylic acid product after hydrolysis with lithium hydroxide. Now in the next step, we form an acyl azide through a CDI activation of this carboxylic acid, and we undergo a subsequent decarbonylation to give us this NH3 product. This is via the Curtius rearrangement that we discussed in last episode, which I'll put a card to here. Now in this next problem, we have another multi-step synthesis, and so we just have to fill in the blanks once again. So in this first case, all we have to do is a ring nitration to give us this nitroarene product. We can then undergo a reductive amination with this pyrrolidine to give us this secondary amide product, the secondary amine product. The secondary tertiary amine product rather, which is a secondary benzylic position. We can then undergo a reduction of the nitro group to afford an aniline. This aniline can then be treated with hydroxylamine, which is able to actually transamidate this ester to give off methanol as a product, and then through subsequent activation and decarbonylation, we're able to afford this 1,3-bis aniline. Now let's get into today's material, 1,2 shifts of boron-containing compounds. So the way I like to think about boron is that it's basically a middleman. It's a chaperone, and it helps get things nice and close so that chemistry can take place. If you have a nucleophile, it will often just attack the boron, and if there's an alpha or beta electrophile, it's in close proximity and it can more easily do displacement from the boron. So originally, when people would think about boron, we typically just think about hydroboration, which is a common undergrad level discussion where we add an H and a boron-containing compound across an alkene, and this is the main purpose where you'd think about boron, and at least it was for me when I first learned about boron in chemistry. But with modern advances, there's a lot of cross-coupling reactions involving transition metals such as palladium with boron-containing compounds for Suzuki reactions and related reactions. And so boron is all the rage. There's CH borylation being discussed, and more ideas with boron are coming out. And so the coolest thing is when you take the modern approaches to generate boron-containing compounds, and then we couple that with some of the ideas of the past, just with our modern spin. And Aggarwal is the leader in this field. So here's some of the reactions that can occur for 1,2 shift type processes in boron-containing compounds. So the oxidation step of a borane in hydroboration-oxidation is a 1,2 shift mediated by peroxide in the presence of base. The Matteson reaction is another example of a 1,2 shift. We can have Zweifel Olefination, which is an additional type of 1,2 shift involving an alkyne, as well as Aggarwal Homologation and Silyl-Aggarwal Homologation, which is just a variant. There's also Silyl-Matteson reactions. So the oxidation step of hydroboration is quite simple, but I don't see it discussed in too many examples in textbooks, so I thought it would be good to list this here. Now I'm not going to discuss too much hydroboration other than just to say it's anti-Markovnikov, so the hydrogen goes to the tertiary position if it's a tertiary position, and the boron goes to the less substituted position in most cases. So what can then happen is you deprotonate hydrogen peroxide, which is a good nucleophile. It attacks the boron to form an 8 complex, which is just negatively charged, like a carboxylate is negatively charged. And then we have a 1,2 shift, which is kind of like Baeyer-Villiger oxidation, but in this case it's a boron instead of a carbon with a carbonyl. This then displaces hydroxide as a leaving group, giving us our boronate product. If you work this up with acid or base, you can typically just cleave off the boron very easily. Now, a couple examples of the oxidation step include the treatment of this chiral boronic ester with hydrogen peroxide, giving us a mixture of diastereomers of the alcohol at this position, but an extremely high yield in the presence of some complex functional groups. Additionally, the treatment of this cyclopropyl boronic ester with hydrogen peroxide afforded this cyclopropanol in very high yield as a single enantiomer. Now, one really cool trick that I am quite impressed with that I wanted to highlight here is you can make aryl boronic acids quite easily. If you make a Grignard or an aryl lithium and you trap it with trimethyl borate, and then you work it up, you'll get the boronic acid. But the cool thing is if you treat this with hydrogen peroxide, you can just do the same oxidation that you do with your typical alkyl boranes, except in this case you get a phenol instead of an alcohol. And so one other example of it is on this pyrazole-containing compound, where we get a hydroxypyrazole derivative. So this is quite a cool tool that you should use more in synthetic chemistry, because you can see that the yields are really good, and that's a common theme throughout this episode for 1,2 shifts of boron-containing compounds. In most cases, great yields are obtained. So the Matteson reaction is as follows. If a boron has an R group, which is just some carbon-containing compound, and it's activated with an alkoxide to form an 8 complex, the R group can migrate and displace a leaving group. So these would typically be like a chloride or a bromide. This way you form a new carbon-carbon bond, but the boron is still retained, so you can do more chemistry with that boron if you want. Now, instead, you could also just take an existing boronic ester and treat that with a nucleophile, a carbon nucleophile such as a Grignard or a lithium-containing carbon, and this will just attack the boron, form an 8 complex, the R group will shift and displace a leaving group, giving us another carbon-carbon bond. So some examples of the Matteson reaction include the treatment of this boronic ester with phenyl magnesium bromide, displacing a chloride, giving us this phenyl product. Additionally, the treatment of this chiral auxiliary boronic ester was demonstrated to undergo a chiral inversion as the leaving group migrates from the opposite face. And this is just kind of a cool strategy overall for installing carbon-carbon bonds. It's kind of like a Grignard reaction on an aldehyde, but instead of an aldehyde, you have a chloroboronate. Now, the Silyl-Matteson reaction is kind of cool because what you can do is you can very easily lithiate the alpha position of silanes and then trap that with a borane. Then, if you make an 8 complex via this addition, one of the R groups can migrate and displace the leaving group as a leaving group. And what you obtain is a carbon-containing system with both a silicon and a boron. And so you could do different chemistry with those 2 different heteroatom-containing groups. So this is a very useful way to introduce diversity, just through a lithiation reaction. Now, the Zweifel Olefination typically affords cis-alkenes via the addition of a hydroboration across an alkyne. So in this case, you can see that we have Z-alkene formed as a product, but it's a boron-containing alkene. If this alkene is then treated with iodine in the presence of base, the base can attack the boron, the iodine can form an iodonium, and then one of the R groups can migrate from the 8 complex, opening up the iodonium. And then in a second step, another hydroxide can attack the boron, forming yet another 8 complex. But in this case, instead of having the R group migrate, the boron-carbon bond cleaves, displacing iodide as a leaving group, and then we form a cis-substituted alkene. In other cases, I guess because this is an alkyne, you can only form cis-alkenes, you'd never be able to form E-alkenes. Now, the cool thing you can do is if you do this instead of with sodium hydroxide and iodine, and you use cyanogen bromide, you actually can get transalkenes. So if you wanted to take this approach and get the opposite type of alkene, you can just switch to cyanogen bromide, which isn't ideal because it's quite toxic, but nonetheless, it's a method that's been reported. So the Aggarwal homologation is a more recent development, which is kind of like the Matteson reaction, but instead of using your typical leaving group like a halide, you can just use a sulfonium ylide to generate your 8 complex. So they've also demonstrated other ylides, such as nitrogen and phosphorus ylides, if I'm not mistaken. So the borane can attack. This then forms your zwitterion, and you can undergo the shift of an R group, displacing this dialkyl sulfide as a leaving group, giving us this boron functionalized product, as well as forming a new carbon-carbon bond. Some examples of this that are really cool include this one paper from Aggarwal's group, where they first lithiate this TMS-containing ethylene oxide. They form this lithiated species, which attacks the boron ester, forming an 8 complex. And this is where it gets really cool. So the R group is able to shift, and when it does so, it opens up the epoxide. But if you have an alkoxide alpha to a silane-containing group, what you can do is you can do a Matteson olefination. And so the alkoxide forms a 4-membered ring with the silicon, which then undergoes an elimination to generate an alkene. So this is a really cool reaction. One example of it from their paper includes the treatment of this N-Bach azetidine, which is converted cleanly to the alkene-containing product. So they essentially just install an alkene with the boron still retained. So the cool thing about all this chemistry is you typically end up with a boron still after, and you can do more chemistry with that, such as cross-couplings, etc. Now, Dave Evans reported quite a cool reaction earlier on, and so in this one paper, what he does is he treats boron-containing azides. He treats alkene-containing azides with boranes, which undergo hydroboration, but then the boron is able to form a complex with the azide and displace nitrogen as a leaving group, and then through a 1,2 shift, you form a pyrrolidine. And so one example from his paper shown here is this hydroboration reaction, which will spontaneously form a complex between the boron and the azide, which can then displace nitrogen as a leaving group, and through the 1,2 shift, we prepare this pyrrolidine product. In this case, after workup with HCl, they get the HCl salt of the pyrrolidine, as well as deprotecting the alcohol, which would have also reacted with the borane. So if you would want any other great references, here's a couple other great references to some of Aggarwal's work. He has some really good reviews, and he's got some cool publications that are related to this area on his group's website that I'd encourage you to check out. So for this lecture, I'm going to assign 3 practice problems. In the first case, just fill in the blanks. It's just a multi-step synthesis here. In the next case, I just want you to predict the product of the following reaction. This is related to the Evans reaction that we just talked about. And finally, propose a multi-step synthesis starting with this aryl bromide to prepare the corresponding phenol. Now you can do this several different ways, but it's probably easiest if you use the chemistry that we talked about today. And so I hope that this has been a useful lecture on boron rearrangements. If you have any questions or comments, I'd encourage you to leave them below. It would really help out the channel if you left a like and subscribed, and I hope you have a great day.